The main series of videos will cover the multiple examples that you will encounter when solving equilibrium problems. This first video is about finding or calculating the equilibrium constant from the equilibrium concentrations or partial pressures. These examples tend to deal with concentrations, but the process for using pressures would be exactly the same. This is the most direct way to find the equilibrium constant value. And what this would look like experimentally is that you would set up an experiment, you would let it go to equilibrium, you would measure the concentration or pressure at equilibrium, and then plug the values in to the equilibrium constant expression. So obviously we're not going to set up these experiments, so what this would look like for you in a problem is that you would be given something. I have two examples for you. So example 1 tells us that at 445 degrees Celsius for the reaction H2 gas plus I2 gas in equilibrium with 2HI gas, the equilibrium concentrations are that H2 has a concentration of 0.11 molar, I2 has a concentration of 0.11 molar, and HI has a concentration of 0.78 molar. So our equilibrium constant expression looks like the concentration of HI squared over concentration of H2 times the concentration of I2. So this shows us exactly where we need to plug the values in. My concentration of HI is 0.78, so that value is squared. And in the bottom, I have 0.11 times 0.11. So you pop this into your calculator and you find that the equilibrium constant value for this reaction at this temperature is 50. And you now know how to interpret this number. So it's 50 means our equilibrium lies to the right. It means that we produced more product than reactant when the reaction reached equilibrium. And that's it for this one. So a more likely scenario, but we're still being asked to calculate the equilibrium constant value. So this is our example 2, and it's the more likely. And this is that we know the initial concentrations and we know the equilibrium concentration of one component. So we don't know the equilibrium concentrations of everything, but we have enough information to determine them. So we're going to do this in 2 ways. Example 2, I guess I technically have 3 examples. So we're going to do a generic version, and then we're going to set up an actual version and come up with some step-by-step things to do so that you'll always do these things in an order that makes sense and gets you to where you need to be. So this generic example, the reaction is going to be A in equilibrium with 2B. Now I'm not going to put whether it's gas or aqueous. We're just going to use concentrations, and neither of these would be a liquid or a solid. So both things are going to appear in the equilibrium constant expression. So we are told that initially A has a concentration of 1 molar, B has a concentration of 0. At equilibrium, A has a concentration of 0.75 molar, and from this information, we can figure out how much B was produced because we have the balanced reaction. So for every 1 mole of A that I use up, I make 2 moles of B. And we can use concentration as a proxy for moles in this case because everything is in the same size container. So if it's a gas, if the volume of the container doesn't change, we can add and subtract pressures just like they're moles. In a solution, if the volume of the solution doesn't change, we can add and subtract molarities just like they're moles. So I used up 0.25 moles of A, or 0.25 molar for our specific units. So my concentration of B, based on the balance reaction, is 2 times the change in the concentration of A. So 2 times 0.25 means that I made 0.50 molar of B. Now, great if that all made sense to you, but there's a better way that we can organize this information that you may or may not recognize, and that is in something called an ice table, or as I have evolved to doing it over the years, a rice table or a rice box, and you'll see what all of these letters mean when we get it set up. So the R stands for reaction. We're going to put the reaction at the top of it so that it's easy to see where everything is. Then there's a row for the initial conditions, and I have those. So my initial conditions are that A was 1 molar, B was 0. The next row will be for the change. And then the last row, I'm going to leave a little space, and you'll see why, is for the equilibrium conditions. I leave a little space because I like to put a line here, because we'll be able to add these columns up just like it is a math problem. So I know that at equilibrium, my A was at 0.75 molar. So in this column, I know exactly what to fill in, which is that my change is that A went down by 0.25 molar. And this is, if I use up 1 mole, which is 0.25 of A, I make 2. So I'm going to add 0.5 of B. And if I started with 0 and I added 0.5, in the end, I have 0.5 molar of B. I have everything I need at equilibrium, so I can calculate an equilibrium constant value from, make that a concentration, my equilibrium constant expression, which is that it's 0.50 squared divided by 0.75. And my equilibrium constant value for this reaction is 0.33. So this is my generic example. We're going to do one more example that uses an explicit reaction and sets up a step-by-step process for this. So our third example, the reaction is that CO gas plus 2H2 gas in equilibrium with CH3OH gas. And we have a reaction mixture. at 780 degrees C initially contains a concentration of CO equal to 0.5 molar and a concentration of H2 equal to 1 molar. At equilibrium, the concentration of CO is now 0.15 molar. And we need to find the equilibrium constant value, and it says Kc. So we're going to use concentrations, which is great because we only have concentration information. So just like every problem you have ever done in math or otherwise, our step one is going to be to fill in the given information. Now, I guess step one is to set up the rice table so we have spaces for all of this. So that's actually what I'm going to do first. So reaction, initial, change, equilibrium. And my reaction is CO plus 2H2 in equilibrium with CH3OH. Initially, I am told CO is 0.5 molar. H2 is 1. I don't get any initial information about the CH3OH, so I can assume that it's 0. If you're given a set of initial conditions and something isn't mentioned, that means that you don't have any of it to start with. Let me get my addition line here. And then I'm also told that the equilibrium concentration for CO is 0.15. So all of these things, I'll put a little 1 by them. I will also change colors for the next pieces, are the given information. Next step, we'll go blue. The next step is to fill in any part of the change row that's easy to calculate. So fill in the easy C. And if you look at this, basically in our column initial change equilibrium, there's only one component that we have 2 out of 3 for. So our CO starts at 0.5, goes down to 0.15, so it went down by, so I subtracted 0.35 molar, but remember, because it's all in the same container, we can add and subtract these just like they're moles. So this value that my CO went down by tells me, because of the stoichiometry of the balanced reaction, how much H2 I used up and how much CH3OH I made. So that's going to be my next step. So step 3 will be use stoichiometry for other C values. So it's 1 mole of CO for every 2 moles of H2. So if I use 0.35 of CO, I have to use 0.70 of my H2. That's going to be a step 3. Now that goes down because it was also a reactant. The product gets a plus sign because I'm making product. And for every 1 mole of CO, I make 1 mole of CH3OH. So this is going to be a plus 0.35. That gets a 3 label because it's our step 3. Step 4, we'll go green for this one, is to complete the equilibrium row. So I have initial and change for everything. I have equilibrium already for one of them. So in the H2 column, 1 molar minus 0.7 molar, I'm left with 0.30 molar. And CH3OH, 0 plus 0.35, I've created 0.35 molar. So this is where, if you have made any mistakes in your stoichiometry, or if you made the reaction go the wrong direction, which is something we're going to talk about in a later video, you will see that maybe you got a negative value here and you can't have a resulting negative value for an equilibrium concentration. All right, last step. Step 5, we have all of our equilibrium concentrations. So last step, calculate KEQ. So our KC, I'm not going to write the expression this time, but you should take some time to practice and make sure you feel good about doing this. 0.35 divided by 0.15 times 0.30 squared. And the equilibrium constant value for this reaction is 26.